Welcome everybody once again. So we will start our module 4. Module 4 is about Kani'S method. Analysis of indeterminate structures using Kani'S method. So in first chapter in our unit 1, module 1, we saw about Clapeyron's theorem of three moments and how to analyze the problems using Clapeyron's theorem of three moments. In the second module, we saw about slope deflection method. So by using the equation 2EI by L, MFAB, that is moment at A when the far end is B is equal to fixed end moment at A. So we saw MAB is equal to MFAB plus 2EI by L into 2 theta A plus theta B. So using this equation, we saw how to solve and analyze a problem, analyze an indeterminate structures using slope deflection equation. This equation is called the slope deflection equation. That was our second module. So our third module was analysis of indeterminate structures using moment distribution method, and we saw this moment distribution method is an extension of slope deflection method. So how to simplify the slope deflection equations. So that was the moment distribution method. Now fourth module is about analysis of indeterminate structures using Kani'S method. So Kani'S method is also similar to moment distribution method because this Kani'S method is also an extension of slope deflection equation. Kani'S method is also an iteration method. So this Kani'S method is also called displacement method of analysis. This comes under displacement method of analysis. Okay, now the Kani'S method, it was developed and given by Dr. Caspar Kani in the year 1947, whereas the slope deflection method was developed by G.A. Manny in 1950. So this we obtained in 1947, given by Caspar Kani, and this is similar to moment distribution method because both Kani'S method and moment distribution method use Gauss-Seidel iteration procedure. So these both uses the iteration procedure to solve slope deflection equations without explicitly writing them down. See, we don't write the slope deflection equation, but we reduce this slope deflection equation into some other form and we solve our problems. We analyze the indeterminate structures. Okay, that is the beauty of both moment distribution method and Kani'S method. Now, the difference between Kani'S method and moment distribution method is that Kani'S method iterates the member end moments themselves rather than iterating their increments. See, you remember moment distribution method. What did we do? In iteration 1, we iterate the fixed end moments with the help of distribution factors. Then the second step, see whatever increments we have obtained, we will iterate that. But in Kani'S method, the fixed end moment itself is iterated in every steps, in every iteration. Okay, that is the difference between Kani'S method and moment distribution method. Now, this Kani'S method consists of simple numerical operations performed repeatedly at the joints of a structure in a chosen sequence. So, with this understanding, we will move on to our next concept, that is how to analyze a continuous beams and frames without joint translation. Okay. So, continuous beams and frames without joint translation. So for this, we will consider a continuous beam. Okay, let us consider a continuous beam. So in this continuous beam, let us take the span AB. See, AB is a part of a continuous beam. So we will consider the span AB of a continuous beam under imposed loads. So now we will draw the deflected shapes. See, if this AB is a part of a continuous beam, the final deflected shape of the span AB will be like this. Okay, if the deflected shape is like this, how can you write theta A and theta B? See, this will be theta A, sorry, okay, this slope, draw a tangent, this slope is theta A, so this slope is theta A. Now draw a tangent at B, so this slope is theta B. Now the moment will be like this. So there will be a clockwise moment MAB at A, and there will be an anti-clockwise moment MBA at B. Okay, so now let MAB and MBA be the moments developed. Theta A and theta B the corresponding rotations at A and B due to imposed loads. Okay, so MAB and MBA are the moments developed. Moments developed in the span AB due to the external loadings, and theta A and theta B are the corresponding rotations at A and B. Now, for this case, the slope deflection equation can be written as, we know the slope deflection equation is MAB. See, for the moment at A, moment developed at A, MAB is equal to fixed end moment at A for the span AB. So, M of AB plus 2EI by L into 2 theta A plus theta B. Okay. Now we will consider this I by L. I by L as K. That is, I by L is the relative stiffness. We know, we have already studied in our third module in the slope deflection, in the moment distribution method, what is the relative stiffness K, right? So K is equal to I by L when the far end is fixed. So A and B are intermediate supports, right? A and B are intermediate supports. So we can take this I by L as KAB. So we will rewrite this equation as MAB is equal to, we will rewrite this equation as MAB is equal to MFAB plus 2E into, we will replace this I by L as KAB into 2 theta A plus theta B. So KAB is equal to I by IAB by L, length of the span AB. Okay, so I by L is replaced by KAB. So MAB is equal to MFAB plus 4EKAB into theta A plus 2EKAB into theta B. Now, this 2EKAB theta B is taken as is the rotational component. Okay. So, this, see this 2EK theta. This is considered as the rotational component, rotational contribution of the ends. That means, see the first case, 2EKAB into theta A can be taken as MAB. Okay, that is for this moment AB, what is the contribution of the rotation at A? So MAB is called the rotational contribution of end A to MAB, and MBA will be equal to 2EKAB into theta B. That is the rotational component. MBA will be the rotational contribution of end A due to MBA is the rotational contribution of end B for this moment MAB. See all these moments, that is this fixed end moment and this rotational contribution and this rotational contribution, all are contributing for this moment MAB. Okay, so this is the fixed end moment. So these moments, this is small MAB, this rotational component is replaced by 2MAB and this rotational component is replaced by MBA. Okay, because this is the contribution of rotational component for MAB due to the rotation at A. This is the rotational component contributing for MAB due to the rotation at B. So we will replace this as 2MAB and this as MBA. So what we get is MAB is equal to, okay, so what we get is MAB is equal to MFAB plus 2MAB, small m. This is small m. The rotational contribution is represented by small m plus MBA. So now we have reduced the slope deflection equation. See, this is slope deflection equation. Now we have reduced the slope deflection equation into Kani'S equation. Okay, so this equation is called a slope deflection equation. This equation is called a Kani'S equation. Now, we all know how to calculate M of AB, right? Now our aim is, how will we calculate MAB, small MAB, that is the rotational components, small MAB and small MBA. So for that, so we know there may be many members meeting at NTA. If there are more than one member meeting at joint A, so that B is the common designation for the far ends. See, for all these, for any members joining at end A, B will be the destination. B will be the far end. That is common destination for far ends. Now for the equilibrium at joint A, we know how to write the joint equilibrium equations, right? So for the equilibrium at the joint A, the algebraic sum of the end moments of all the members meeting there must be equal to 0. See, we know how to write the joint equilibrium equations. So if this is A dash, B. What is the joint equilibrium equation? MA dash plus MAB will be equal to 0. That is nothing but sigma MAB is equal to 0. That is summation of algebraic sum of end moments of all the members meeting at A will be equal to 0. Okay, so if B is an intermediate support, summation of all the moments meeting at B will be equal to 0. So now, what we get is sigma MAB will be equal to 0. So if sigma AB is equal to 0, see, for simplification, we are considering only one member is joining at A. So if only one member is joining at A, sorry, not like that. It is sigma B. Because B is the for this case, B is the common destination. So sigma B of MAB is equal to 0. So that means this equation, that is the Kani'S equation. We will take this as equation number 2. This is slope deflection equation as equation number 1. So from equation number 2, we get sigma B of MFAB plus sigma B of 2MAB plus MBA is equal to 0. So because this is equal to 0, if MAB, summation of all the members of joining at A, MAB is equal to 0, that means this is equal to 0. If left hand side is equal to 0 in equation number 2, the right hand side is equal to 0. So what is sigma B? It is the sum taken over all the adjacent joints B. Okay. Sum taken over all the adjacent joints B. Now, let MFA. Now we are taking another term. See, already we have taken the terms MFAB. MFAB means fixed end moment at A in the span AB. Now, we will consider the term MFA. MFA means this is the resultant restrained moment. At A. And that is equal to algebraic sum of all the fixed end moments at A. So this resultant end moments, see, when you are taking this span, the fixed end moment at A, you will have MFA dash and MFAB, right? So MFAB. This summation is called the resultant restrained moment at A. That is a summation of all the fixed end moments at A. Summation of all the fixed n moments at A is called resultant restrained moment at A. So MFA will be equal to sigma B. Sigma B means the far end is B, the destination is B, of MFAB. Summation of all the fixed n moments meeting at A. So now what we get is, we will take this as equation number 3. So from equation number 3, we get we will write the value for this, that is sigma B of MAB is equal to, that is this small MAB is equal to, we get minus 1 by 2 into MFA plus sigma B into MBA. Okay. See, because this is replaced by MFA. This sigma B MFAB is replaced by MFA. So we will take this as equation number 4. So substituting 4 in 3, we get sigma B of this small MAB is equal to minus half of MFA plus sigma B into MBA. Now, we will take this as equation number 5. This equation number 5 gives the algebraic sum of rotational contribution of all members meeting at A. Okay. This is MFA, that is restrained moment at A. This is a rotational component at A. Now, we know this small MAB. See, we have already obtained this small MAB is proportional to its K value. It depends on the stiffness K. So, the individual share of the members in the total rotational contribution can be found by distributing the total rotational components in proportion to their K values. Therefore, when you are considering the member AB, so what happens is, for the member AB, that is the rotational component, MAB becomes KAB by sigma B KAB. This is nothing but the distribution factor. KAB by sigma B KAB is the distribution factor into the summation of far end is B, destination B, MAB. Okay. So, what we get is MAB is equal to, you substitute this equation number 5 in equation number 6. So, we get minus half of KAB by sigma KAB upon B multiplied by this MFA plus sigma B MBA. So, MFA plus sigma B MBA. BA. So this value, see, this is replaced by this minus half of KAB by sigma KAB is replaced by RAB into MFA plus sigma B into MBA. So this is important while solving the problem for using Kani'S method. That is RAB. This RAB is called the rotational component. RAB is called the rotation factor. So MAB. RAB is called the rotation factor. MFA is the resultant restraint moment. MBA is the rotational contribution. The rotational contribution due to the rotation at B for the span AB. Okay, that's all. So I hope now you understood. See, what we have studied is, we are writing the slope deflection equation. From the slope deflection equation, we are reducing it to Kani'S equation. So in Kani'S equation, MAB is equal to fixed MFAB plus 2 small MAB plus MBA. So fixed end moment is calculated as usual. This MAB and MBA are called the rotational contributions of the span AB. Rotational contribution for the span AB. So here the joint is A, right? So the rotational contribution for the span AB at joint A due to the rotation at A, due to theta A. And this is the rotational contribution at A due to the rotation at B. Okay, see, these both are contributing for joint A. If it is MAB, it is the moment at A when the far end is B. So both these are contributing for the moment at A. And this is the rotation due to theta A and this is due to theta B. That is the meaning of that. Now, in order to find how to find MAB and MBA, we have determined. So we have assumed many conditions and we have found that this rotational component MAB will be equal to the rotation factor multiplied by the restraint moment plus the rotational contribution. That is the meaning of that. Okay. So what is MAB? MAB is called the rotational contribution to A due to theta A. Okay, rotational contribution to the end A due to theta A. That is MAB. So RAB is called the rotation factor. So rotation factor, that is equal to, this rotation factor is equal to minus half of KAB by sigma KAB. That means rotation factor is equal to minus 0.5 times of distribution factor. Now, capital MFA. So, MFA is the resultant restraint moment at A. This is the resultant restraint moment at A and is equal to the algebraic sum of the fixed end moments at A. Okay, algebraic sum of M F AB. Algebraic sum of the fixed end moments at A. That is the resultant restrained moment at A. And what is MBA? See, this is sigma B into MBA. So, sigma B into MBA means it is the summation of the rotational components, at B. Okay. So, MBA we know. Okay. And this will be obtained from the iteration process, the previous iteration. This should be obtained from the previous iteration. Okay. So, this is important. So, the important things here is we should know the slope deflection equation. We should know the Kani'S equation. So, and we should know how to calculate MAB. So, for calculating MAB, we need these things. So, now with this understanding, we will move on to our problems. So, before moving to the problems, we will write the steps also. Steps required for calculating, for analyzing the Kani'S method. So, procedure for Kani'S method. See, and one more important thing, forgot to tell here. So, this is for the case AB. So, how can you write in general? See, general cases Mij is equal to Rij into Mf of I plus sigma j of Mji. Okay, this is the general case. So, you replace A by I and B by J. Okay. Now, we will move on to for the procedure for analysis using Kani'S method. So, our step 1 will be as usual to calculate the fixed end moments. So, calculate fixed end moments by assuming all the supports are fixed. So, if the supports are fixed, there will be negative moments. So, left will be anti-clockwise and right will be clockwise. Now, depending upon the external loadings, we can calculate the fixed end moments. Okay. So, we calculate the fixed end moments, and in Kani'S method, you have to enter these fixed end moment outside the outer square or circle. So, in the procedure, see there in moment distribution method, we calculated is using moment distribution tables. Here we don't have tables, we have either square boxes or circular circles. So that means, see, if you have a span like this, A, B, C and D. Okay, if you have the span like this, see, B and C are intermediate supports. That means you will have, very, very important, you will have one smaller box and another bigger box. This is for joint B. Now for joint C, you will have another small box and another bigger box. This is for joint C. So you have to calculate this fixed end moments. So fixed end moments, it is MFIJ, right? MFIJ. You will write it as MFAB, MFBA, etc. So these MFIJ, it should be entered in the outside, the outer circle, outer square of the circle. Okay, so outer square, so inner square and outer square. So you have to write the moments here, right? So MF. See this, there will be A, this is B, joint C and joint D. So you will be writing MFAB, MFBA, this is MF. This is MFBA. Here you will be writing MFAB. So MFBC, MFCD, sorry CB. This is MFCB. MFCD and MFDC. So after finding the fixed end moments, you have to write these values in outside of the outer box, outer square box. Okay, that is your step 1. Now step 2, calculate K values and rotation factors. That is step 2. So step 2, calculate the stiffness K, then find the distribution factor and find the rotational factors. So after finding the rotational factors for all the members meeting at each joint, okay, so the rotational factors will be, if you have A, B, C, D, you will find the rotational factors for B and C. So these values are entered outside the first circle. So this is the first circle, inner circle or the inner square, inner box, right? So you have to write, see for the joint B, you will have the rotational factor for BA and BC. So you have to write the rotational factor R, BA here, rotational factor BC here. At joint C, you will have rotational factors CB and CD. So you have to write the rotational factor CB here, rotational factor for CD here. Okay. So that is your step 2. Find the rotational factor and write it in the outside of the inner box. Now we will move on to step 3. After writing this, we will move on to step 3. So step 3, find the resultant restrained moment at each joint. Find the resultant restrained moment at each joint and enter these values of resultant restrained moment within the inner square of the circle. We know resultant restrained moment is, how will we calculate it? Is as M F I, right? We will calculate it as M of I. For joint A, it is M of A. For joint B, it is M of B. For joint C, it is M of C. It will go on like that. Okay. So you calculate. That means you can add the summation of M of BA and M of BC. So you add these both M of BA and M of BC. That is your restrained moments at B. So that will be written as the restrained moments has to be written inside the inner box. That is MFB here. Here you will be writing MFC. Add these both. You will get M of C. Now we will move on to our fourth step. So step 4. Step 4, compute the rotational contributions. So we know the rotational contributions means it is Mij, which we have obtained in the last step in our procedure, right? MAB, Mij. So now we need to find, in the step 4, we need to find Mij. Okay, so we know Mij will be equal to Rij into Mfi plus summation of Mji. Okay. So after finding this, by using Gauss-Seidel iteration equation, you have to iterate some 5 or 6 iterations until you get the closer results. And these values you have to write. You have to put a line, see? Put a line. And you have to write. Here you will be calculating MBA, MBC, MCB and MCD. This goes on depending upon the number of iterations. First iteration, second iteration, third iteration, fourth iteration, etc. So for every iteration you have to find MBA and MBC. Okay. So that is all. See, if you understand this, how to write this, your problem will be over. So first of all, find the fixed end moments and write it in the outer box. Find the rotational factor and write it in the inner box. Find the restrained moments. Then using the equation, find the rotational contributions. This is rotational contributions. Okay. So fixed end moments. Right here, fixed end moment is your first step. Finding the rotation factor is your second step. Writing the restrained moments is your third step. Finding the rotational contributions is your fourth step. Okay. Now step 5. So step 5, using the Kani'S equation, determine the moments, determine the final end moments. So what is the Kani'S equation? MAB will be equal to MFAB plus 2MAB plus MBA. So this is Kani'S equation. Using this Kani'S equation, we can calculate the final end moments. That is our step 5. So this is the procedure for calculating analyzing the indeterminate structure using Kani'S method. So in the next class, we will solve the problems using Kani'S method. Thank you for today. Thank you for listening.